This video is on section 1.2 notes, special applications of ratio and proportion. So first we're going to talk about scale drawings, and when we talk about scale drawings, it's going to be important to know what the scale factor is. So the scale factor is a ratio that describes how much a shape or object has been enlarged or reduced in size. So our first example of this is imagining that this would be some sort of real car, and then this is a drawing of the car. So the real car is 16 feet 6 inches in length and 6 feet in width, and then the drawing of the car is 4 inches, 4 1/8 inches in length and 1.5 inches in width, and so it's been reduced in size. Or you could say from the drawing to the actual car, that's been increased in size. So to write our ratios, we're going to do the actual length of the car divided by the drawing length and the actual width of the car divided by the drawing width. And if you remember from the last set of notes, section 1.1, whenever we set up ratios, we need to have the same units. And right now we have inches for the drawing, but we have inches and feet for the actual car, and we don't want to have mixed units. So we're going to convert these feet units into inches. And so if I have 16 feet, I'm going to do 16 feet times 12 inches per foot, plus another 6 inches. That's 198 inches. And then 6 feet times 12 inches per foot is 72 inches. Okay, so the actual length is 198 inches divided by the drawing length is 4 1/8 inches. The actual width is 72 inches. Divided by the drawing width is 1 1/2 inches. Inches, or you can do the marking for that. And so this is the ratio of the lengths. And the ratio of the widths. And then this equation comparing the two is our proportion. So if I want to figure out what the scale factor is, or the common ratio is another word for it, then I just need to reduce these ratios. So I can do 198 divided by 4 1/8, 4 plus 1/8. Notice I'm putting that in parentheses. This is one way to type it in. And I get 48 is my ratio. So 48, or 48 over 1, would be my scale factor, or my common ratio. So it means that the car itself is 48 times bigger, or it's enlarged by 48 times in comparison to the drawing. I can also verify this with 72 divided by 1 1/2, or 1.5, and I can see that that's also 48. So if you have those kind of mixed numbers where you have a whole number and a fraction, you can always type it in like that, 4 plus 1/8, and just make sure you put it in parentheses. Another way to type it is 198 divided by, and then these calculators have a way to type in different types of fractions. You can hit the green button, alpha, and then y equals, and to type in 4 1/8, you would use the second option. So divided by 4 1/8, and then it puts the parentheses for you, and you get 48. So the other option would be you could do 4 plus 1/8, 4 plus 1/8, let me fix that, and find the decimal ahead of time, and then you could do 198 divided by the decimal. So you have a few different ways to type that in if you're uncomfortable working with that mixed number there. Okay. The next example says, suppose that a rectangular room has a length of 18 feet and a width of 12 feet. An architectural scale drawing of this room is made so that on the drawing the length of the room is 4.5 inches. What will the width of the room on the drawing be? What is the scale factor? So we have to make sure that we're using the same units when we set up our ratios. And so starting with, we have the 18 feet. I'm going to convert that into inches. So 18 times 12. And I'm going to go ahead and write down this math that I'm doing since these are notes and I want to have all my work shown. So 216 inches for the length, and then 12 times 12. I know that off the top of my head, that's 144 inches for the width. And so I'll go ahead and write my proportion. So I have 216 inches over 4.5 inches. There's my length ratio. And for my width ratio, I have 144 inches divided by x inches, the width of the drawing, which is what I don't know. And then I'll go ahead and cross multiply to solve my proportion. So 216 times x equals 4.5 times 144. $648. And then I'll divide by 216 to get the x alone. And I get 3. So the width of the drawing is 3 inches. And then if I want to figure out the scale factor is 216 over 4.5. Or, so again, it's 48, or 144 divided by 3 would show me the scale factor as well. Again, it's 48. So the scale factor is 48, or you could say 48 to 1. All right, another special application of ratio and proportion is similar figures. So comparing two figures that are similar in shape, but one of them has been enlarged or one of them has been reduced in size. And so you can always write ratios to compare the sides that are similar, and you can write proportions to compare those sides to each other. So here, if we were comparing the width to the length, you can see we're comparing the bigger width with the smaller width, the bigger length with the smaller length. Over here, we have 4 sides that are different, and so we're comparing all of those. They've got the bigger shape in the top of the ratio and the smaller shape in the bottom. But they're comparing, like, W is compared to T, X is compared to P, and so on. So if we have a cylinder here, a bigger cylinder and a smaller cylinder, and we know that they're similar to each other, then we could find the missing altitude, which in geometry, oftentimes they use the word altitude for height, and they're using the letter H to represent it. So find the missing altitude of the cylinder, and so we'll go ahead and just compare these. So I'm going to do this diameter. I'll do a ratio of the diameters, bigger divided by smaller, equals the altitude, bigger divided by smaller. And so I'm comparing the bigger diameter with the smaller diameter, the bigger altitude with the smaller altitude, and then overall I have a ratio of my diameters and a ratio of my altitudes. And so I'm keeping everything organized. And I'll cross multiply. So I've got 1.5 times H equals 6.3 times 3 1/4. And when you multiply this, we have a couple different ways to multiply it. I'm going to do 6.3 times 3 plus 1/4. A lot of you probably know that 1/4 is 0.25, but if you don't, this is probably the quickest way to type it in. 20.475. So 1.5 times H is 20.475. and then I'm going to divide that by 1.5, divide that by 1.5. So I'm going to hit divide by 1.5, 1.5, and I get the altitude, or the height of the larger cylinder, is 13.65. And everything that I was doing was in terms of inches, and so this is inches. Right, on the next page of our notes, it says we have a landscaper who's designing a garden for a house that is not yet built. He needs to determine how long a shadow the house will cast into the garden area. To determine this, the landscaper, who is 6 feet tall, measures his shadow to be 8 feet long at a particular time on a summer afternoon. If the roof line of the house will be 15 feet high, where the landscaper was standing, how far from the edge of the house will the shadow extend at the same time of day? So we're using similar figures. We're using triangles here to determine how far the shadow of the house is going to go. So we'll do a proportion using the man, the height of the man compared to the height of the house. So 6 compared to 15, and then the shadow compared to the shadow. So 8 compared to S. So we're doing the height versus the height, the shadow versus the shadow, and we're doing small divided by large, small divided by large. So we're keeping all the information together. And then I'm going to go ahead and solve this proportion, and I'm going to cross multiply. So 6 times S is 6S, and then 8 times 15. And then to get the S alone, I'll divide by 6. And I get that the shadow is 20 feet. So at that same time of day, when the man had a shadow of 8 feet, the house itself would have a shadow of 20 feet because the house is taller than the man is. All right, next we're going to look at 2 different types of proportions. The first is direct proportion, the second is inverse proportion. So 2 quantities are directly proportional if an increase in one quantity leads to a proportional increase in the other quantity, or if a decrease in one leads to a decrease in the other. And this is what we've been looking at with the proportions that we've done so far. The man, if we compared a man with a house that was taller, then the shadow that he had was longer because the house was taller than he was. When we looked at a picture, we had a car. We had the length of the car and then the length of the car in the drawing. Well, if we looked at the width of the car was less than the length of the car, and so the width of the car in the drawing was less than the length of the car in the drawing. So something got bigger, then the other thing got bigger. If something got smaller, then the other thing got smaller. It just made sense. So that's what direct proportion is. And so this first thing we're going to do is going to be like, yep, we've been doing that already. So for example, it says the electrical resistance of a wire is directly proportional to its length. The longer the wire, the greater the resistance. If 1 foot of nichrome, I don't know what that is, heater element wire has a resistance of 1.65 ohms, what length of wire is needed to provide a resistance of 19.8 ohms? So we're going to have 2 things that we're comparing. We're comparing the length with the resistance of the wire. So we're going to have 2 lengths. We're going to have 1 foot in length, and we're going to have X feet, the amount that we don't know, and then we're going to have the resistance. And the first resistance that we have is 1.65 ohms, and then 19.8. So we're going to have our length, ratio, and we're going to have our resistance ratio. And what we know is that we have the first scenario, the second scenario, first scenario, second scenario. So I'm keeping all of my information organized as I set this up into a proportion. So as the length increases, the resistance is going to increase. So first length increases, resistance also going to increase. This is a direct proportion. This is what we've been doing the whole time. So at this point, it's just going to feel like we added another example to our notes of what we've already been doing. So to solve this for the unknown length, I'm going to go ahead and cross multiply. So x times 1.65 equals 1 times 19.8. And then I've got 19.8 divided by 1.65 to get the x alone, and I get 12. And the x was the length, so 12 feet. So if 1 foot is a resistance of 1.65 ohms, then 12 feet would be the resistance of 19.8 ohms. All right, inverse proportion. This is the part that's going to feel a little bit different. Two quantities are inversely proportional if an increase in one quantity leads to a proportional decrease in the other quantity, or if a decrease in one leads to an increase in the other. So note here is always invert the second ratio. It doesn't really matter which one you invert as long as you invert one. And when we use the word invert, I mean to flip the second ratio or flip one of the ratios. Okay, so here's what we mean when we say inverse proportion. If you're driving and a certain trip that you're taking takes 2 hours at 50 miles per hour, then if you were to take the same trip at 60 miles per hour, you're not going to say, well, I'm driving faster, so it's going to take even longer. That's not how driving works. You would say it's an inverse relationship. If it takes 2 hours at 50 miles per hour, then if I drive even faster, then it's going to take me less time. So the speed increases, but my time decreases. That's what inverse means. Something goes up, something goes down. So what we're going to do is we're going to have one ratio that talks about the amount of time that it takes, that has hours as our units. We're going to have another ratio that compares our speed, but we're going to make sure that we flip one of the ratios because we want to have an inverse proportion, not a direct proportion. So I'm going to have 2 hours compared to X hours. And I'm going to have 50 miles per hour compared to 60 miles per hour. But because this is an inverse proportion, I have to flip the second ratio. So I'm going to say 2 hours to X hours equals 60 miles per hour to 50. So if it was direct, then I would do it the way I always do it. I would say the starting information and then our new information, starting information divided by new information. I would say I'm comparing the time with the time, I'm comparing the speed with the speed, except here we're dealing with inverse. And so that means I need to take one of the ratios and flip it. So now that I've done that, now that I've inverted the second ratio, I'm going to go ahead and solve it by cross multiplying. So x multiplied by 60 equals 2 multiplied by 50. So 60 times x equals 100. And then I'll divide by 60. So x is 1.6 hours, 6 repeating. And I'm going to go ahead and take away the 1 hour here. This number right here, this is a fraction. It's 2/3. 1 2/3 hours. Or if I want to figure out how many minutes that is, I can multiply this by 60 because there are 60 minutes in an hour, so times 60. So this would be 1 hour and 40 minutes. So if we were driving 50 miles per hour and it takes us 2 hours to get somewhere, then if we speed up and we go 60 miles per hour, it might take us 1 hour and 40 minutes to get there instead. We go a little bit faster. All right. So here are some other popular inverse proportions, and with these they gave us specific formulas in the textbook, and so with these we don't have to worry about inverting the second ratio, because if you pay attention, they inverted it for us. So here they're comparing speed with one ratio and the teeth of a gear with the second ratio, but instead of doing A over B, where you have gear A and gear B, they've already inverted one of them. The same thing here, they're talking about speed and they're talking about teeth in a gear, but here we've got the drive shaft and the rear axle. Here we've got the axle and the drive shaft, so they've already inverted one for you. Here we've got pulley A and pulley B. We've got the speed that we're comparing and the diameter that we're comparing, but you'll notice they've already inverted one of them for you. So these are just some inverse proportions that we have, and then they've got some formulas that they've given us to work with. So it says because gear A in this drawing has twice as many teeth as gear B, so this is gear A, this is gear B, when B makes 2 turns, A will only make 1 turn. If B rotates 20 turns per second, gear A will rotate 10 turns per second. The speed of the gear is inversely proportional to the number of teeth. So for example, if gear A turns at 40 rotations per minute, what is the speed of gear B? So we're going to say 40 rotations per minute for gear A, so 40 RPM. Then the speed for gear B is what we're solving for. And then the teeth for gear B is 8 teeth. The teeth for gear A is 16 teeth. And then to find the speed of gear B, we can go ahead and cross multiply to solve this. So I'm going to do B multiplied by 8 is 40 multiplied by 16. So 8B equals 640. And then to get the B alone, I'm going to divide by 8. And the speed of gear B is 80 rotations per minute. In a car, the speed of the drive shaft is converted to the rear axle motion by the ring and pinion gear system. Again, gear speed is inversely proportional to the number of teeth in the gear. So for example, if the pinion gear has 9 teeth and the ring gear has 40 teeth, what is the rear axle speed when the drive shaft turns at 1200 rotations per minute? So the drive shaft turns at 1200, so the drive shaft speed is 1200 rotations per minute. We want to find the rear axle speed. It says the teeth in the ring gear is 40 teeth divided by the teeth in the pinion gear is 9. And we're going to go ahead and cross multiply. So R times 40 equals 1200 times 9. $10,800. And then to get the R alone, I'm going to divide by 40. 270. So the rear axle speed is 270 rotations per minute. And then pulleys transfer power in much the same way as gears. If the larger pulley is twice the diameter of the smaller, then when the smaller makes one turn, the larger will make 2 turns. The speed of a pulley is inversely proportional to its diameter. If pulley B is 16 inches in diameter and is rotating at 240 RPM, what is the speed of pulley A if its diameter is 20 inches? So speed of pulley A is what we're finding. The speed of pulley B is 240 rotations per minute. Diameter of pulley B is 16 inches. Diameter of pulley A is 20 inches. And then we're going to go ahead and cross multiply to solve. So A times 20 is 240 times 16. $3,840. And we'll go ahead and divide by 20. So the speed of pulley A is 192 rotations per minute.